Hey everybody, today I'm teaching by candlelight and I'm going to show you some applications of the cross product. Let's get started. There's a lot of different applications for the cross product. The primary reason that you might want to use the cross product is to create perpendicular vectors. We're going to use that in a little bit in an example that helps us define the orientation of a plane. Remember, that's kind of the slope, if you will, of a plane. And so some other applications for the cross product, you can use it to measure the angle between vectors. There's a formula similar to the dot products formula with cross products. The length of the cross product is equal to the length of A times the length of B times the sine of the angle between them. And so if you want to calculate the angle between two vectors, you can use this, or you can use the dot product. The dot product's simpler. But you can also use this to tell if two vectors are parallel. If you simply cross them and you get the zero vector, then that means those two original vectors are parallel to each other. It's another reason you might use a cross product. It has a geometric application in finding areas. And so we'll use this in a second to find the area of a parallelogram that two vectors form. And there's a lot of different physics formulas that have the cross product at their heart. Anytime when you only care about the perpendicular component of two forces, if they're at angles to each other or something like that, then you can use a cross product to calculate them. For instance, the torque calculation in physics is force times radius. There's a bunch of other ones that you'll probably see if you take physics someday. So let's look at a specific example. So I don't think I need to be quite that big. That's a little creepy. All right. So here we have a parallelogram with two different vectors. This is the vector A, which is one step over and three steps up. This is the vector B, which is 6 steps over. And those two vectors form a parallelogram. And sometimes it might be worth knowing what the area of that parallelogram is. To do that, all you have to do is find the length of the cross product, which is kind of 2 steps. Find the cross product first and then calculate its length. So let's start by finding the cross product of A and B. So A cross B, well, I'm going to use the i's and j's definition of this vector. This is 1i plus 3j, and I'm going to cross that with 6i, and so that would look like this. We can use the distributive property, so I times 6i is 6i, and 3j times 6i is 18j crossed I. Remember, the order is important. And if you remember the ijk wheel for determining cross products, if you go forward through that cycle, I crossed with j, crossed with k, and so forth, versus backwards, that's how you can simplify these a little bit. I crossed with I, just like anything crossed with itself, is 0. J crossed with I is going backwards through that cycle, and so that gives us a negative k value. And so simplifying this is nothing, and this is 18 times negative k, or negative 18k. And so now we've found the cross product of these two. If we find the length of the cross product, that's going to be equal to the area of this parallelogram. And so in this case, this is a one-dimensional vector, and so its length is simply the absolute value of this. And so its length is 18, and what that means is the area of this parallelogram is also 18. For a little bit more challenging question, let's see if we can find the angle. If you watch the dot product video, we've already done this problem, and so you might remember that the angle is about 71 degrees, but we can find that using the cross products angle formula. This is the length of the cross product, which we just found, by the way, was 18, is equal to the length of A times the length of B times the sine of the angle between them. So the length of the cross product, that's 18. Oops, that's not the right one. Not sure if I can find it. So anyway, we'll make a new box here. 18. So the length of the cross product is 18. The length of A we can find, that's 1 squared plus 3 squared, and take its square root. So 1 and 9 is 10, square root of 10 there. The length of b, since b is a one-dimensional vector, it's just the absolute value of that is 6. And so if we take this equation, we can rearrange it and solve it for sine of theta. And so if we do that, sine of theta is equal to 18 divided by root 10 and 6. And that is, on a calculator, it's about 0.9487. And so if you wanted to find the angle then, this would be an inverse sine calculation. The inverse sine of 0.94 is approximately 72 degrees. So there's how you can find an angle. I do believe that the dot product formula is a little simpler to work with because generally finding a dot product is really easy, whereas finding a cross product is kind of a pain. But anyway, let's look at another example. So in our last example today, we're going to have to find the plane that goes through 3 different points. And so before we get to this problem, let's just talk a little bit in general about how do we do this. In general, 2 points form a line on a 2D surface, and 3 points generally define a plane. And so how do you find the equation for that plane? In order to do that, you'll have to first find a couple of vectors that are on the plane. And you do that by looking at some of the points that are on the plane and subtracting them. Once you've found a couple of vectors that are on the plane, then what you need to do is use those to create a normal vector. A normal vector is a vector that's perpendicular to the plane. And guess what? That's where the cross product comes in. You take 2 of those vectors you just formed and cross them, and that will create a normal vector. Once you have a normal vector, you put that normal vector into the plane equation. So the plane equation, remember, is ax plus by plus cz. So you put those 3 numbers in for a and b and c. And in order to determine the last number, the d, that is based on how high or low the plane is, you plug in a point to find that. So that's the general procedure we're going to find in this example. Now, this example is a bit of a beast. I'll tell you, there's a lot of steps to it, so it'll take the rest of our time today. First of all, before we get too bogged down with some actual, calculations, let's take a look at what this looks like. So here are those 3 points plotted in GeoGebra, and I'll just put this into motion. You see that those 3 points form what looks like a triangle kind of floating into space. And if you extended that triangle in all different directions, that would be the plane that we're trying to find an equation for. So that's the goal. Our first step is going to be to try to find some sort of vector that connects R and S, or R and T, or T and R, or T and S. We need some vectors that lie on that triangle, on that plane. And so let's get started. So we can find a bunch of different possibilities. We could find the vector RS, or R and T, S and T, T to R. Any combination of those will work as long as we have 2 unique ones that aren't parallel to each other. So we wouldn't be able to do RS and SR, for instance. For this example, I want to choose RS and ST. And so let's look at how we find RS a moment. Remember, to find a vector from R to S, we're going to do a subtraction. We're going to do -1 minus 3. So -1 minus 3 is -4. In other words, we went backwards 4 steps to go from 3 to -1. To go from 4 to 0 was also going backwards 4 steps. And to go from 5 to 10 was going forwards 5 steps. If we include the normal I, j, and k components, this would be -4i minus 4j and plus 5k. Now let's figure out how to get from S to T. To go from -1 to 2 is to increase by 3. And so we'll write 3i. To go from 0 to 1 is an increase of 1, so plus 1j. And to go from 10 to 9 is a decrease of 1, which is minus 1k. So now that I've got a couple of vectors that are on the plane, I need to find a cross product of normal vector. And so to do that, let's take these two vectors and find their cross product. So to do that, I'm going to speed things up a little bit. Instead of showing you an entire another cross product calculation, I'm going to use my handy dandy vectors program that I put into my calculator. If you're in my classes, you might have a spreadsheet that you could use to calculate the cross product, or you can do it by hand. It's not the end of the world. But let me do this a moment. So I type in the first vector, which is -4, -4, 5. And then I type in the second vector, which is 3, 1, and -1. And it gives me the length and the dot product. And there it is, the cross product. Can you see that? Oops. Anyway, I'll read it to you. It's -1, 11, and 8. So the cross product here is -1i plus 11j plus 8k. So now that I know the cross product, what that's given me is a vector that's perpendicular to that triangle. And more importantly, that is the orientation of our plane. These three numbers, -1, 11, and 8, are the a and the b and the c in our equation. So let me put them in a second. -1 and 11 and 8. All that's left to do now is to calculate what d is. And in order to find d, I need to take one of the points that my plane goes through. Any one of these, r, s, or t, should do, and plug them in temporarily for x and y and z, and calculate what that gives me. So, well, let's try that a moment. We've got -1 times, I'm going to use point r, so I'm going to use the 3 from the x component there, plus 11 times 4, plus 8 times 5. We'll see what that all equals. That's -3 plus 44 plus 40. And so that would be 84 minus 3 is 81. So that's what D ought to be, 81. Now, if we've done everything correct, we should be able to use any of the 3 points here, and it should give us 81 as well. So let me just really quick try this again with point T, and if it works, I'll be thrilled. And if it doesn't, you'll realize that Mr. Rohr is human and messes up too. And it'll be up to you guys to find in the comments what went wrong. So -1 times 2 is -2. 11 times 1 is 11. 8 times 9 is 72. If we add these three together, I'm hoping it's 81. So 11 and 72 is 83. 83 and -2 is, in fact, 81. And so that means we either got really lucky and the 2 points both worked, or this really is the equation for the plane that goes through those 3 points. So anyway, there is another application for the cross products, and hope you enjoy using them as much as I do. Have a wonderful day.